and we don't quite have example 4 up here because we had to cut it off since we've got too much information on this page, so we had to lose the words example 4. Sorry about that. But we're in example 4. Ballistic pendulum is one way to measure the velocity of a bullet fired from a gun. So a ballistic pendulum is a big, heavy thing sitting on like this, right? So it's on a rod, and there's this thing here, and then a bullet will come in here, and so it's going to impart its momentum, and the thing will swing up. So it winds swinging up, just like we've got here. Bullet goes in here, lodges itself in, and once it's lodged itself in, it puts some momentum into it, and the ballistic pendulum will continue to swing up. So it's one way to measure the velocity of a bullet fired from a gun. A bullet is fired into a large mass on the end of a pendulum where it lodges itself. By measuring how high the pendulum rises, we'll be able to figure out the velocity of the bullet before impact. How do we do that? We'll get to that. So, denote the bullet's mass as mb, the pendulum's mass as mp. Assume the pendulum's rod's mass is negligible, so all we have to worry about is the mass of the block, mp. And the height it will achieve will be h. So it goes up some height h. Now, using all these things, which we could actually do, if this were real life, we could build something like this, and we could have a pencil on the edge so it would mark how high it went up, and we'd be able to weigh the mass of the bullet. We'd be able to weigh the mass of the pendulum. We'd be able to find a fairly lightweight, strong rod that was able to hold it in place without being much compared to the mass of the pendulum, and we'd be able to actually do this. So there's a real way to figure these things out, and this is what people did in the 1700s. So, all right. Now, what's the trick that we're going to use to be able to solve for this? So momentum isn't going to be conserved throughout this entire thing, right? The momentum of the bullet, as it goes up, well, we've got gravity that's dealing against it, right? So gravity is an external force from the point of view of momentum. If it's moving up, it's going to have some force moving it up. So we've got external forces on the bullet, right? We've got external forces happening here. We're dealing with gravity. Momentum's not going to be conserved. But at the same time, energy isn't going to be conserved. We've got this impact. We never said it was we never said it was elastic, and it's certainly not going to be an elastic collision. This is an inelastic collision. This is definitely an inelastic collision. So we can't conserve energy throughout. We can't conserve momentum throughout. How do we do this? We can conserve them one piece at a time. So notice, the instant, if we break this into 3 things, the bullet goes in, and at this moment, while it's still just after the collision occurs, before it's had the chance to start swinging up, momentum is conserved. So we'll have momentum initial equals momentum final. Then from here, once it's swinging up, there's no impact occurring, there's no more collisions, it's just a basic pendulum rod going up, which we can then do as energy. And then from here, energy initial will be equal to energy final. So from there, we're able to do it. So we're able to break this into 2 pieces. The momentum is going to be conserved for just the collision, and then after the collision, energy will be conserved. So we break it into 2 pieces beforehand and afterwards. So if momentum initial is equal to momentum final after the collision, what's in the initial momentum? Well, the mass of the bullet times the velocity of the bullet. Is there anything else moving? No, we've got the pendulum at rest. So mass of the bullet times the velocity of the bullet. And once again, we're gonna nix those vectors because we're going to be only dealing with linear quantities. Wait a second, I hear you ask. Isn't it going to be moving up and to the right when it swings up? Yes, that's true, but we'll be dealing with what that is energy, so when we get to that point, we'll only have to worry about speed. So for the collision, as far as we're concerned, it hits and goes in, and it's still basically moving in just one dimension because it lodges itself very quickly, and the collision happens very quickly compared to the movement of the swinging. So mass of the bullet times the velocity of the bullet is equal to, so what's the final momentum? It's the whole system put together, right? It's the mass of the bullet plus the mass of the pendulum, and now the velocity of the system put together, right? So velocity of the whole system put together. For ease, we'll make this velocity pendulum. So velocity system after collision we'll denote as just simply velocity pendulum. So that makes it a little bit easier to write because we're going to have to be talking about 2 very different worlds. The world of the impact and the world after impact where we're swinging. So this will make it a little bit easier on us. So velocity pendulum. But it's important for us to pay attention to what we're doing here. So we can figure out what the velocity of the bullet is in terms of mass of the bullet plus the mass of the pendulum divided by the mass of the bullet times the velocity of the pendulum. But we're not able to solve for this. We still need to find out what the velocity of the pendulum is. We don't know what the velocity of the pendulum is. Remember, we only have the height is what we're going to have to figure out. So now we start looking in terms of energy. So if energy initial is equal to energy final, well, the energy in the system at the beginning of the swing, does it have any height? No, we can consider that as its baseline height. Is it moving? Yes, it's definitely moving. Are there springs involved? No, there's not any springs. The only thing we've got there is the kinetic mechanical energy. We've got kinetic energy. So 1/2 the mass of the system. What's the mass in this case? M1 plus, sorry, not M1, but M bullet plus M pendulum times what's the velocity that the thing's moving at? The system after collision. So velocity of the pendulum now squared is equal to, so when it gets to the top of its arc, is it moving still? No, if it's at the top of its arc, it's got to have just finished moving. So the only thing it has is stored potential gravitational energy. So mgh. M in this case isn't just m, it's the mass of the whole thing, mass of the bullet plus the mass of the pendulum, times g times the height that we've achieved. So mass of the bullet plus the mass of the pendulum, boom, it's on both sides. We can cancel out. So we've got the velocity of the pendulum squared is equal to 2 times gh. Velocity of the pendulum is thus equal to the square root of 2gh. We can substitute that back in, and now we've got the velocity of the bullet is equal to the mass of the bullet plus the mass of the pendulum block divided by the mass of the bullet times the square root of 2gh. And there we are. By just measuring the height that the thing goes up to, by already knowing the constant for gravity, by weighing the mass of the bullet and weighing the block, we're able to figure out the velocity of the bullet, which is pretty great, because these are all the things that we'd be able to do in the 1700s. So even without fancy technology like lasers and all these other cool stuff, we can actually come up with a really solid way to measure the velocity of a bullet by what we know about momentum and what we know about energy. Great. Hope you enjoyed this. Hope it made lots of sense. I'll see you again at Educator.com later.